Okay, now you're not gonna find a formula that tells you what to do here. I mean, you could go to the whole thing about resistance and the rules for parallel resistances and stuff, but we're not talking about that. That's easy. There are formulas. We want to talk about why. Okay. So here's our situation. All these distances are the same. Well, that's what I said here. Okay. It's a uniform wire throughout. Okay. I'm going to figure out the ratios of current I3 to I2 and I3 to I1. Okay. So people have trouble with this because you have to think rather than pull out a formula. Okay. You can make this into formulas and you can derive the formulas for parallel resistances from the whole concept. Now, the concepts that we have are potential gradient. Okay. And the fact that, that we also have current density. Okay. And the potential gradient determines the current density. The current density and the diameter of the wire determine the current. Okay. So those are concepts that you really need to have. And you go all the way back to what we observed with the heat flow through that stack of hinges or whatever it was, okay, plates. As you go right there and you get the whole idea of a current density. That should be totally locked in because we did it in lab. And we'll probably go a little bit further with that idea. Okay. In lab Friday, if I remember to turn on the heat source. All right. So what we know about is a gradient. And conductivity give you the current density and density with cross-sectional area gives you current. Now that should be totally intuitive, totally locked in. When you look at a circuit, you need to understand that. Otherwise, you're doing middle school physics. Okay. So this requires some thought, some understanding, and not just a series of formulas. Although there are formulas you can put together, it's much easier to get the idea and use the idea to figure out your proportionalities. And that's a higher level thinking. Not that combining all the formulas isn't high level thinking. It is. Okay, but that's even harder than understanding what you need to understand to answer these questions. And you lose concepts when you start just pulling formulas together. And it's important to be able to do both. Right now, we're working at the conceptual level, and then we're going to get formulas that'll actually make sense. All right. So we have kind of this logic. Potential gradient, current, conductivity. I got to probably just combine notation. Says with using the arrow bigger. So these two go together, give us current density, and combine that with cross-sectional area, you get current. Okay. Now again, uniform, homogeneous. I should have put in homogeneous, same material throughout. Okay. It's kind of implicit. It really shouldn't state. Simplest possible case. All right. So what do you have to do? Well, conductivity, since the wire is homogeneous, you've got constant conductivity, so you don't need that. All you need is potential gradient to start working this out. What can you say about potential gradients? If you're looking at trying to get I3 over I2, and I gave you that one because that's the easiest one and that's the one you want to focus on, right? If I ask you for I3 over I1, you'd have to do a little more work, and I didn't want to put that much of a challenge on you. Okay? What I did was enough. And you did, pretty well with that. Uh, Finally, after I said, I think somebody said, well, the kernel split equally. I said, well, I've got 3 centimeters between here and here, and put 10 miles of wire between here and here. Is the current going to split equally? Clearly not. Okay. Why not? Because the potential gradient is going to be bigger in the shorter wire. Okay. I said, well, why is that? You're still missing a connection. You said potential gradient is going to be greater in the shorter wire. Yeah, that's true, but you haven't told me why. How can you possibly justify that? There's one step that's necessary to justify that assumption, which is the potential here doesn't change, potential here doesn't change, potential from here to here is what it is. So the potential change between C and F doesn't depend on whether you go through this part of the circuit or this part of the circuit. Okay. Now you can say that, well, this part of the circuit has 3 times the length, so it's got 3 times the potential gradient. But if you don't see that the potential drop is the same from here to here, you're losing an important insight that you're going to need when we get our hands on some circuits. Yeah, we all had our hands on some circuits, so you can apply it to what you've already seen in lab. Okay, is that making sense? So the logic of this, it's very simple, but you have to put every bit of every piece into it in order to satisfy what you need, and not to satisfy me, but that satisfies me because then I know you have what you need to think clearly about circuits. Okay. So it's not so much whether I'm satisfied or not as whether you have thinking skills you need to apply. Okay. So here's our reasoning. Notate it like this without having to write out too many words. Potential difference between C and F is always the same. So if we start with a C and end with an F, it doesn't matter what we have in between. But this indicates that the direct path from C to F has the same potential change as the path CD. Okay, parallel path. The length. If I see up, CDEF, I'm going to just declare that that means the length. There are notations I could use, but it should be clear what I'm talking, right? This path is 3 times as long as this. Okay. It follows. So I'm going to say ECF equals 3 times ECDEF, E being the potential gradient. But the potential gradient is the electric field, so I call it E. Okay. Now you can fill that in as you will. I'm not making it potentially a little bit or intentionally a little bit obscure, but I'm not being too careful to make my notation completely transparent. Why do I have a 1/3 here and a 3 here? Okay. Well, it's because your electric field is inversely proportional to your potential gradient, but you need to think that. Okay. I'll probably make a note to that. And I think I said that wrong. Um, Potential gradient is inversely proportional to the length, assuming you have a uniform homogeneous wire. So there's some logical connection. Now, with those logical connections, you should be able to answer these 2 questions. Now, this one takes a little bit more thought. This one should be pretty obvious. So, going to give you a couple more minutes to think about it. It's a nice day. I'm going to walk around from one door to the other. And I'm just doing that because I don't want to look over your shoulder while you're thinking about it. Okay. I don't mind taking a hike, but I just don't want to stand here. I don't know if I make you more nervous when I'm out strolling around or when I'm watching you, but I kind of think the latter. Okay. So I'll be back in like 2 minutes. Incidentally, I think it took me 136 seconds. I said I'd be back in 2 minutes. Okay. I counted my paces, but the clock out in the commons there, whatever area you call that, was playing some tune. It sounded familiar, but I couldn't make out the tune. So I had to count my paces while I was trying to figure out that tune. So I'm not sure my count was specifically correct, but I was pacing, I think, very close to 1 pace per second, just a slow pace. All right. Now, the reason I say that is it's kind of amusing. But you wouldn't think with perfect clarity about what this ratio is. And no one would be trying to figure out what that dang tune is while you're counting your steps. Okay, there's an analogy. So I finally asked, I came in, well, what'd you get? And I got the answer, it's easy when taught. Okay. I made the comment, yeah, it's easy once you see it. It's just like the old woman, young woman picture. You're familiar with that? Look it up. Google it. It's a meme that you need to carry through your whole life. Okay. And everything you think about. It's a picture that looks like an old woman or a young woman, depending on how you look at it. And then if you cross your eyes a little bit, look at it a little different, also the picture of a young woman is in there too. Okay. And maybe it's a different thing. Okay, well, my point is thinking that you have to do this, all of a sudden it becomes clear if somebody gives you enough hints. How do you get it when you don't have hints? You're an engineer, you got a problem to solve. How are you going to solve that problem? Okay. Now you have all the pieces, and you pretty much have all the pieces, but you weren't seeing them all. You saw quite a bit. But the one piece you didn't see was potential difference is the same if you go here as here. And you think potential gradient, and you have 1/3 of the potential gradient. So you have 1/3 of the gradient. Okay? One way or another, you put these pieces together. Then you tell me what the ratio is, and somebody told me 3. Well, if I had give you all the hints, I'd say that's good for half credit. But that's not the ratio I asked for. Why is it 3? Because of the ratio of the lengths, what I got. Well, the ratio of the lengths is 3. Length, this goes through is 3 times as great as the length this goes through, but it's an inverse proportionality. And you really want to think in that term, in those terms, okay? So it's going to be 1/3. You have 3 times the length, therefore you have 1/3 the potential gradient. Okay, therefore you have 1/3 current. All right. Now, how do you use that then? Can you use that to get this ratio? Did you get that ratio? Let me pause a second and see what you think. Okay, now in getting the I3 and I1, I got an answer well before times 3. Because this path has 4 times as much wire in it as this. Well, that doesn't work. Okay. Because this current is equal to this current, and it's a bunch of stuff. I don't want to get into all the details of that, but the key is, and I dropped the hint, current doesn't accumulate in water. Okay, and people seem to and locked in on that when I said it the last 100 times. And why? Why does current not accumulate in a wire? It's because you have 3 charges in that wire. If you got more charge density here than you have here, then this charge is going to repel itself into this region. And the current or the density of your charge carriers has to be constant. If you have any area where the density is greater, the charges there are going to repel themselves into the areas where it's less. Okay? They can't get any closer together than they are. The density of your charge carriers has to be constant because they're free to move. There's nothing restricting them from moving to the greatest possible distance. And that's what they do. Okay? So make sure you've got that idea. That's a central idea. Okay, now, that tells you, since all this is just plain old homogeneous charge carrying wire, it's got some resistance, whatever that is, predicting reciprocal conductance. Okay. So the fact that current can accumulate tells you how I1 is related to I2 and I3. So what do you think that relation would be? So took us a little bit to figure out what happens to the charge that drift by any point of I1. And the charge that drifts by here is in a given time is the same as the charge that drifts by here because that's what current is, how much charge drifts by a point. Okay. You take the drift velocity and the charge density and the cross-sectional area of the wire, you get the current. And I think you've got that idea at least ready to be locked in. Okay. You want to really think about that. You've been dealing with this model of conductivity for 2-3 weeks now. Okay, so whatever drifts by here has to drift by here. Well, I mean, it's all drifting. The electrons that drift by here maybe never get to here because maybe the current cuts off well before you drift from here to here. And maybe this is 10 meters. These things are drifting at a millimeter per second. Okay, so it takes 10,000 seconds for any charge that's here to end up here. And you don't know where each charge ends up because their paths are so complicated and random. There's an overall electric field that keeps these things drifting, a cloud of electrons drifting at a constant speed, as long as your voltage stays the same. Okay. long as your potential gradients stay the same. Now, so the rate at which charge drifts by here is the same as the rate at which charge drifts into this node area where the thing splits, right? And where does it go? Well, some of it goes here and some of it goes here. None of it gets lost. Total amount of charge drifting through here and here is the same as the amount that drifts into the node. Whatever drifts out had to drift in. And anything that drifts in has to drift out. Okay? Now you know enough to answer this question. So I'm going to give you 2 more minutes. Maybe a little less than 2 because I'll step just a little faster. But I want you to put this together and tell me what I3 over I1 is, or is I1 over, it's I3 over I1. Okay, no, nobody has an answer I have a lot of confidence in, but I'm not sure what the answer is going to be until I write it out. Okay, well, so I3 over I1. What? Well, I1 equals I2 plus I3, right? That's what I just said. Current that flows in here flows out. What flows out? I2 and I3. Okay, so if once you have this, you know that you can write I3 in terms of I2, right? And I'll do this for I2 equals 3 times I3. Because you've already figured out I3 over I2, okay, is 1/3. So I3 is 3 times I2. Oh, wait a minute. I2 is 3 times I3. And you know that because same potential 3 times as far, this has got to be 1/3 the current of this. So you have it symbolically, if you've written out what I2 and I3, what the ratio of I2 to I3 is. So you do it symbolically, we can do it intuitively. So equals 3I3 plus I3, which is 4. And I think somebody told me it's going to be 4 times as much. When I asked why, I didn't get what I regarded to be a clear answer. Okay, it was just based on lengths and stuff like that, total length. So you can think about whether that really works. That answer, total length and stuff, didn't totally connect to what's really going on. Okay, so I think of that. So I3 over I1 equals. I think I've got to stop the thing. That didn't make any sense. The more from over here. Because this is only a small part of what comes in through I1. Okay. Makes sense? Okay, so again, want to think in terms of potential gradients, which is electric field. Don't forget to think in terms of conductivity, which I left constant here. Okay. And cross-section areas, which are constant. So you have a fairly straightforward set of connections. Now, a what diameter ratio do you need if you wanted I2 to equal I3? Okay, so since said 3 times diameter ratio, because right now it's carrying 1/3 as much current. If you triple the diameter ratio, that'll give you 3 times the current. No, triple the diameter ratio, you get 9 times. But the thinking is good. Just, you don't seem to understand how area and diameter are different things, and they're closely related. The ratio of areas is the square of your ratio of diameters. So the ratio of diameters is square root of the ratio of the areas. Now let's work out the logic here, okay? First of all, you still have the same potential gradient if you got the same length. Same length, same potential difference, right? We usually have 1/3 the current. I should have an intermediate step between here and here. I'll just say, from all this, um, so interspersed between here and here, you have same current density. You have originally 1/3 the current. So 3 times the cross-sectional area. That's a CS there for cross-section. Pretty small, maybe a little hard to read. But the logic is pretty clear. Same potential gradient, undeniable. Because it's the same length and the same potential difference. So you have the same current density, since the current density in homogeneous wires, they're still homogeneous, is directly proportional to the potential gradient. So you need 3 times the area. So it's the square root of 3 times the diameter. Okay. I mean, how do you get the area? Pi r squared or pi d squared over 4. Okay, the pi is the same, 2 diameters. So just the ratio of the squares of the diameters is the square of the areas, so that the ratio of the diameters is a square root of the ratio of the areas. Okay. Now you really have to understand that. You can't even think about a lot of things if you don't understand that. You might be able to pull formulas out and pretend to think about them, pretend to understand them, but you don't if you don't understand proportionality. Okay. And since I won't attempt to put a percent on it because it depends on field, but I'll say maybe in university physics course, um, I'm guessing 80% of the equations that you use imply proportionalities. Okay. Yeah, there are other aspects, that like, the equation that you get here is not a proportionality. Okay. There's a lot of things that aren't proportionalities, but what is gravitational field? Okay. It's inverse proportion to the square of separation. It is proportional to the product of the masses. Okay. You don't understand it if you don't understand that. You might be able to do it. You might be able to write out the equations. You might be really good with the equation. And there are mathematicians who are really good with equations and don't have a clue what they mean. At least compared to other mathematicians who understand meanings deeply but can't throw equations around as well. And it's the same with engineers. Okay. There's a balance, and different people have different balance. Bottom line is you pretty much need both. And I think engineers need more conceptual understanding than ability to do creative things with equations. Okay, now I'm sticking my neck out on that because I'm not an engineer and I don't understand everything about engineering, although I went to school. 3/4 of people, my friends, were engineers. Okay, that still doesn't qualify me to tell you much with any authority about what engineers need. Okay, when I say these things, they'll say, ask your engineering professor. Smith said this. Think that holds? If it does, come back and tell me. I don't like to say things that aren't true. I think there's something to be thought about there. Well, out of that digression, understand thinking process. The mathematics is trivial. I mean, the symbols and everything. Okay, you write this stuff out in symbols, and it's algebra 1 level. Okay, but the ideas behind it are the challenge. Now, to move on just a little bit here, because we've only got about 12 minutes left, I could start varying these questions. Okay, what if the conductivity here is twice the conductivity of this, and I want to equalize these currents? Well, if I got twice the conductivity, then I only need half the area because I'm going to get twice the potential or twice the current density. Okay, double the conductivity, I double the current density, so then I only need 1/2 the square root of 3 times the diameter. And once you understand proportionalities, then you get some real insight into it's a primitive conduction model. I mean, conduction is really a quantum mechanical process. Very few engineers go to the quantum mechanical research engineers, depending on the research and materials, stuff like that. And other things that I don't understand because I don't do any of that stuff. What's conductance? Okay, let's think about conductance. I'm not sure what I've recorded, what I did. Remember when I turned that thing off? Okay, so I think I'm all right. I think I recorded what I had. I didn't remember turning the phone off. So let's say conductance is potential. Conductance times potential difference is the current. Conductance is how well it conducts. You multiply that by the voltage and you get how much current. It's a pretty intuitive idea, more intuitive than resistance. Okay. So that's why I've been talking a lot about conductance, because you can reason it out with one less step than you need to reason out resistance. Okay? You can reason all this stuff out pretty easily once you understand the proportionalities. There's one more proportionality involved with resistance. The resistance is a reciprocal conductance. So resistance three times, okay, the resistance here is three times the resistance here. Okay, now that is a fairly intuitive concept, but it's not as directly related to the fundamental concepts of conductivity, of current. Okay, fundamental concepts are current density, okay, conductivity. Of course, conductivity would be the reciprocal of resistivity, and resistivity is reciprocal conductivity. It's a conductivity of copper. What's a resistivity to copper? I think resistivity, which is the one I remember, is around 3 times 10 to the 8, negative, no, 3 times 10 to the eighth ohm meters. Well, one makes sense, the other does not. I don't think that works. Okay, that's somewhere in that range. I think it's 3 times 10 to the negative 8. Now it'd have to be 3 times 10 to the 8 because it's in meters, which is cubic meters over square meters. I need to write it out, talk about it. So, okay, hadn't really thought about it. But it's pretty easy. Okay, well, if conductance times potential difference equals current, then using the traditional symbols, conductance, there's your potential difference, there's your current. Okay. And now you get in with the traditional symbols and the frequent form of Ohm's law, V equals IR. Now, it's really easy to get that confused. It's really easy to put I in the denominator, it needs to be in the numerator or whatever. Because until you develop a really good sense, even when you develop a really good sense of how these things are related, it's real easy to screw up the symbols. Okay? But if you think in terms of conductance times potential difference equals current, which is a very intuitive idea. Conductance is reciprocal of resistance. You can always get to this. Even to forget, is it V equals IR, or is it I equals VR, is it I equals V over R, or what? Okay. So we can represent this circuit as This segment of wire has some resistance, which we call maybe R1. This segment has a resistance, which we might as well call R2, this one R3, and here's an R4. Now, I never asked you what the current was here in terms of everything else, but it's not the same as I1. Because I1 branches, but then it comes back together and the charge can't accumulate. So the charge moving past, total charge moving past that point always has to be the same. Okay. No, points here, you got to add this to this. Those are your principles. Now you've got this, and you have rules for resistance. Okay. Parallel components. I'll just say the conductivity to add up. Sorry, the conductances add up with conductivities. Okay. In other words, between here and here, we've got the same voltage. Between here and here, no matter whether we go this way or this way. The current here is this conductance times the potential difference, right? And the current here is this conductance times the potential difference, and that has to add up to the total current. So you have this or just the parallel component. Just for this component of the circuit. And that just becomes a single resistance. So you take this, say that has resistance R. Okay. And if you solve this for R, you got to do the reciprocal of the whole thing, and you get R2, R3 over R2 plus R3, and you can do that algebra very easily, and you should. Okay. You know, just take the reciprocal of both sides or whatever you want to do, and multiply through by a common denominator, R1, R times R2 times R3. And work it out. Then the total resistance here, turns out you just add three resistances. Okay, and we're out of time, so I don't want to detail that with the concept of conductivity. But you should think about it. Okay. Make sense? You want to understand the conductance model. Well, to think through all these steps without having to memorize formulas. Then, of course, you should memorize the formulas. Okay, so you have the best of both worlds. Okay, we'll see you in lab on Friday. I hope to find my Helmholtz coil so I can show you something really neat. Otherwise, we're going to have to build some. But one way or another, we'll do it.